We've talked about how to make 0D, 1D, and 2D nanostructures. So we've already been mentioning some of the special carbon nanostructures, but this lecture has a little bit more of a focus on just them. So first of all, there's lots of different types of carbon nanostructures. There's buckyballs, which are the zero-dimensional nanostructures. There's nanotubes, and there's a distinction there between the single-walled carbon nanotubes and the multi-walled carbon nanotubes. The multi-walled nanotubes are kind of like the Russian dolls, where there's a doll within a doll within a doll. It's like a smaller diameter carbon nanotube encased in a slightly larger one, and you can picture that. Graphene is a single layer of carbon atoms. It's like a sheet of connected carbons. So carbon structures have a lot of different properties. There's graphite, like your pencil lead, which is a metallic conductor. There's diamond, which is actually a semiconductor. They have, if you've got a long chain of carbons, they can have insulating properties. And like I've already mentioned, there's lots of different structures. So first let's talk about these carbon fullerenes, or buckyballs. Again, they're zero-dimensional because they're less than 100 nanometers in all three dimensions. Usually they have 60 carbons. There's some pictures down here below, but some of them can have 70 or 76. They can have different numbers of carbon atoms and still be stable, but they have to be 60 or larger. Every carbon site on a carbon 60 buckyball is equivalent, meaning it's bonded to 3 other carbons. They have the same average bond length. There are 20 faces that are shaped like a hexagon and 12 that are shaped like a pentagon. I also have a model in the class that it would be great for you to look at if you missed this day. The diameter is less than a nanometer, 0.7 nanometers, or 7.1 angstrom. The name came from the man Buckminster Fuller. Yes, that was his real name, and he was an architect. He developed the geodesic dome. You've probably seen this dome before. You may recognize it from the Epcot Center in Disney World. There's a place at the Missouri Botanical Gardens that has one, Climatron, and there's also the Biosphere Museum in Canada. These structures are really cool because they actually enclose the greatest amount of volume while taking up the least amount of surface area, which means from a construction point of view, you're using the least amount of material and yet giving the most amount of space inside. The architect designed these hoping that it would actually allow large numbers of inexpensive homes for soldiers to live in that were returning from World War II. The buildings are also pretty tough. They can withstand high winds like those found in hurricanes. How do you make buckyballs anyways? Well, one way is laser ablation, which is literally taking a laser and vaporizing graphite. There's also something called plasmic arcing, which involves electricity, and you allow these electrons to jump, and basically there ends up being a deposit of buckyballs on the cathode. You can also just burn things, like in a campfire, for example. There are buckyballs that are being produced naturally. What about carbon nanotubes? There are similar methods when they're making carbon nanotubes. They can also bake some in the NOVA video clip that we watch. You're going to see that. There are some electrochemical methods that are used to make them, so there's a lot of different techniques, and you may come across some Science Daily articles that have more recent methods because they're trying to make these at a lower cost and for them not to be so hard to make them straight. The tricky part is keeping the carbon nanotubes straight. There are different conformations that can form, and they have different names based on how the carbons are arranged. You can see here the armchair kind of looks like a lazy boy armchair if you trace the carbons, versus the zigzag. Not so much, it doesn't do that. It goes up, down, up, down, up, down. And then there's chiral, which is kind of a combination of the two rolled diagonally. Imagine like a chicken wire, and depending on which way you roll it, those carbon nanotubes will have different properties from one another. Carbon nanotubes are pretty cool because they're very robust. The carbon-carbon bond is extremely strong, one of the strongest bonds in nature. And the nanotubes are flexible, so they don't break when they're bent. They're very good conductors of heat and electricity. This is what is causing them to be looked at for replacing silicon transistors. So there's a lot of different potential applications of carbon nanotubes. Finally, you might have heard of MEMS before, microelectrical mechanical systems. Well, they're working on NEMS, which is very similar, just nano-electrical mechanical systems. And I encourage you to do some research on this because somebody once did their nano on the news on this topic, and it was pretty interesting. Also in class, we watched a scene where we got to see carbon nanotubes being made and basically being played with, and it's pretty cool.